industrial process, accurate and reliable temperature measurement is an essential feature. In order to achieve that, the performance and range of temperature measurement values must be known for any given thermometer. The experiment was carried out by measuring the temperature reading of water during processes of heating and cooling over various temperature ranges, while using various temperature measuring devices.
We're going to talk about the response of different senses and their effect on the accuracy of our thermal readings. The glass thermometer took for the temperature to stabilize relatively really quickly. However, it is prone to human error because you have to read off the temperature directly from the glass. The PT100 industrial thermometer took relatively similar time as the glass thermometer for thermal stabilization, and the results are much more accurate because the results readings are digital instead of reading it off the glass. The PT100 reference thermometer as well took quite short amount of time to reach thermal equilibrium and is very similar to PT100 IND as well. Thermocouples took the quickest time to stabilize when it came to heating and the longest time when it came to cooling, and it's similar to be set for thermistors as well. However, thermistor outperformed thermocouples, and it does make sense because in industry thermistors are being used more instead of thermocouples.
Now our results showed that for the heating process, the thermistor with a much thinner 3mm sheet gave a quicker temperature response. However, when it came to cooling, the PT100 IND with this much thicker 10mm sheet was able to stabilize much quicker. Now we assume that the thermistor is much better as it has a thinner sheet, so it gives quicker temperature response.
We also have had to compare results from the both platinum resistant thermometers, the effect of the sheet on sensor responses as well. The PT100 Ref has a thin sheet of 2mm sheath, and PT100, the industrial one, has a thick sheet of 10mm. The results for both thermometers were similar, but on some occasions the PT100 Ref performed better. This could be because of that PT100 Ref has a thinner sheet, so the effect of the temperature change was detected sooner. Generally, both platinum resistant thermometers performed equally well at detecting temperature changes quickly.
The mercury glass thermometer can only function with a range from -37 degrees to 356 degrees Celsius, which is a small range compared to uses for any industrial applications. And the readings are prone to human error as mentioned previously. Also, there's a risk of breaking the glass and releasing the toxic mercury, which is quite bad obviously for the human health. So the most useful use for mercury glass thermometers is for laboratories. The PT100 industrial thermometer is by far most common resistant thermometer used in industry because it works perfectly when it comes to measuring small fluctuations and functioning in robust processes as well. It is made out of platinum and can detect changes from -200 degrees up to 400 degrees Celsius. And some thermometers can even sample 3 times per second, which indicates high response rates. The PT100 thermometer also has a thicker sheath, so has a higher lifespan because it is protected from abrasive reactions and can function in high temperature, so it's probably the best one to use in industry. The PT100 reference thermometer is very similar to PT100 industrial thermometer, and the best thing about it can measure the temperature directly instead of you trying to relate the resistance to the temperature, and can function between -200 degrees to 850 degrees Celsius.
Right, thermocouples function by producing a voltage-dependent reading on temperature, which can then be interpreted. And now, industrially, it's very good because it does not need an external power source because it is self-powered. However, it has got some limitations, and this is that it's always off by 1 degrees. Now, it measures a range from -50 to 740 degrees, and is used industrially for measuring temperatures for kilns, gas turbines, and diesel engines. So it's well suited for robust processes. Now, thermistors, on the other hand, have a temperature range from -50 to 300, and it's mostly used in the food industry so that we can control food quality.
So we also had to look at the difficulty surrounding designing a thermometer sensor for an industrial application, where fast responses and robust design are both considerations. The thermometer must be precise and prone to least errors possible. It must function over a wide range of temperatures as well. Thermometers in robust process must have a thicker sheet to protect the thermometer, however, that reduces its response time. So we have to make a compromise of the thickness of the sheath used to maintain fast response time vs longevity.
During the experiment, we took 2 consecutive readings for a single time value, leading to inaccuracies as there could be changes between the time of switching from one reading to another. The results from the thermistor and the thermocouple for a specific temperature change that corresponds with the readings from the PT100 ref and the PT100 IND may not be as accurate as the experiment had to be run twice. It would have been better to record all 4 results during the same experiment so to make sure they all corresponded.